This tech talk is called Supercharge Your Development Time with ArmNN and ARM Compute Library. So in this presentation, we're going to unpack some of the latest features and optimizations which we are bringing out in the ArmML software release of 2011, and also doing a couple of demos demonstrating the performance gain that could be achieved when using these libraries.
Okay, I can take the next slide. All right, yeah, welcome everyone to part of our AI Virtual Tech Talk series. You are listening to or about to listen to today's, which is Supercharge Your Development Time with the new ArmNN 2011 release. Next session is going to be February 23rd, and this is going to be hands-on with PyArmNN for object detection. That will be done by me and my team, actually. And then March 9th, we will be going over automate TinyML development and deployment with Keekso AutoML, and that'll be done by our AI partner, Keekso. So definitely check all those out. Feel free to sign up. The link is there. Next slide. And today, from the ArmNN side, we have Ronan Naughton, Jim Flynn, and Gianmarco Iodice. And they will be going over how to optimize your workflows with ArmNN. Take it away, Ronan.
Yeah, okay.
Also,
go ahead.
Sorry, please save questions for the end. I will help be facilitating those at the end, but go ahead and put them in the Q&A section, and we will go over them at the very end. All right, sorry. Go ahead now, Ronan.
No problem, Carla, and thanks everybody for joining us on this tech talk. So Jim is the ArmNN engineering manager based out of Galway, Ireland. Hello, Jim.
Hey, how's it going?
Not too bad. Working from home today, I see.
Yes, today and every other day.
Very good. And Gianmarco, how are you today?
Hello, Ronan. Very good. Thank you. Looking forward for this talk, honestly.
Good. So Gianmarco is the ACL staff software engineer in the machine learning group based out of Cambridge. And those guys are going to help us with the Q&A later. And them and their teams have put in a lot of effort to get this demo up and running for today. So thank you very much, guys. Okay, let's jump into the presentation. So first of all, we're going to look at some of the objective of this presentation is to show some of the features and optimizations that we have in our software stack. So to look briefly at the software stack, this is the software stack for accelerated machine learning when using ARM processors. It's important to state that this is the software stack when doing acceleration using a Cortex-A CPU or a Mali GPU or Ethos-N NPU. If you're using an embedded target like Cortex-M or Ethos-U, we have a parallel stack which can be used in that scenario using TFLite Micro and Ethos-N. So please check out some of the other tech talks on this. But this tech talk is still relevant for you. So if we look at the software stack, you can see at the top part here is essentially your application. So this is the application specific to you for your use case and your market segment. Now, if you want to do neural network processing, you will most likely have a runtime component from one of the frameworks, be it TensorFlow-Lite, PyTorch, or if you're an Android user, you'll be using Android NN API. Underneath that then is where we introduce the ARM software stack. And the first part of that is ArmNN. Now, ArmNN is an inference engine for CPU, GPU, and NPU. And essentially, it bridges the gap between existing neural network frameworks and the underlying IP. Beneath that, then, we have ARM Compute Library. And that is essentially a machine learning library which provides a range of neural network optimizations and kernels specific to ARM hardware. The optimized neural networks are then compiled at runtime using on-device compilers and then run on the underlying hardware. Now, it's also important to say on the right-hand side, we have a suite of tools which allow you to do optimizations on your neural network models even before you run them through the software stack. This way, you can optimize the models specific to your use case or specific to your target IP. Okay, so we've now taken a look at the stack. The question is, why would you use ArmNN and ACL, even though you're using an existing framework solution today? First thing to mention is that it's versatile and portable, okay? So you can easily target multiple platforms from a single code base, be it CPU, GPU, or NPU. And this reduces the development time. And you can keep your existing framework, so you don't have to throw that away. ArmNN and ARM Compute Library plugs into your existing framework and provides you the performance benefits for ArmNN and ACL. And it's easily deployable across a range of different platforms. If you're using Android, Linux, or bare metal, you can use the exact same stack. Now, we provide superior performance, essentially best in class across a wide range of popular networks. And we use advanced network optimization techniques, workload tuning, and gem heuristics to ensure best performance. Now, there are a lot of other generic math and ML libraries that exist out there, but ARM Compute Library is specific to ARM architectures and microarchitectures. We utilize .product in version 8.2a, and obviously we have specific microarchitecture optimizations like for the Cortex-A 53. Importantly as well is the ARM software stack is the first to adopt new ARM technologies. So if we're talking about SV, which is Scalable Vector Engine, these will appear first, and the optimizations for these will appear first in ARM Compute Library. So if you're an early adopter and you want to use these technologies, you can use our software stack to get the benefits immediately. So that's the reason why you would use our software stack, but how good is the performance? Well, the next slide illustrates, just as an example, the performance of ArmNN against a number of different industry performers. So we've taken 6 different industry software libraries, and we've compared a bunch of libraries here, a bunch of models here against each other. And what you can see here is that for Inception v3, the performance using Cortex-A is 2.1 times faster than the industry average. And similarly for Mali GPU, it's 1.7 times faster than the industry average. And the same is true for other neural network models. So how do we achieve this superior performance? Well, the key is that we only optimize key operators in the most popular networks. We do not support all operators, and we do not optimize all operators. We only focus on the things that are most prevalent in the most common networks. We add new operators with each Android release, and we use advanced network manipulation techniques used to improve performance. Okay, so previously I mentioned that the ARM software stack plugs directly into our existing framework. So how exactly does that work? The next slide illustrates this. The ArmNN SDK and the underlying ARM Compute Library can plug directly into the various frameworks for Linux or Android. So starting from left to right, what we'll see is that if you're using TensorFlow-Lite, you can plug in the ArmNN SDK. How this works is you export a TFLite flat buffer file, and then you ingest that into the ArmNN SDK via parser, where an internal graph is built up and it's ready for processing. If you're a PyTorch user, the experience is similar. You export an Onyx flat file, and this can be taken into the ArmNN parser. Now, if you want to use ArmNN at runtime, you can use Android NN API for Android environments, and that has support for the ArmNN and ARM Compute Library, providing best acceleration on Android. Alternatively, you could use TensorFlow-Lite on Linux or Android, and this allows you to plug in ArmNN using the ArmNN TFLite delegate. Okay, so the delegate is a new thing that we have released in our November release 2011, and I'd like to unpack that a little bit further. Okay, so the ArmNN TFLite delegate allows you to do inference on Android and Linux. Now, how would this work? Well, like I said before, you have your application, which is specific to your needs, highlighted here in the yellow box. Within that application, you will generally have a TensorFlow-Lite runtime component. Now, we want to enable the use of the ARM software stack. So in order to do this, we use the ArmNN TFLite delegate, which plugs directly into TensorFlow-Lite runtime and doesn't have any messy dependencies or anything like that. What does this mean? Well, it unlocks ARM-specific CPU and GPU optimizations for TensorFlow-Lite users. If you're a TensorFlow-Lite user today, you can get the power of ARM optimizations by simply plugging in the ARM software stack into your existing solution. Now, previously I mentioned that we don't support all operators, and we only optimize the key operators. So what happens if we have an operator that isn't supported? Well, in this scenario, the TensorFlow Lite runtime calls out to its delegates and it asks, what operators do you support? The delegates respond and inform the runtime of what operators they support. Based on this information, the TensorFlow Lite runtime partitions the graph appropriately, and it pushes the graphs that can be accelerated through the ARM software stack down through ArmNN, and the parts which can't be accelerated, it pushes them through the TFLite CPU reference implementation for the Cortex-A CPU. Why does it do this? Well, the beauty of this is that all TFLite models can now be accelerated through ArmNN, and unsupported ops can be handled by the TFLite runtime. And this enables performance and greater operator coverage. Essentially, it's a holistic solution for a TFLite user. Okay. The next thing I'd like to talk about is Debian packages for ArmNN and ARM Compute Library. Now, we brought these out to address a pain point in terms of building the ARM software packages. And to address this, by launching the Debian packages, it really has made it so much simpler. With the 2008 release, which is the August of 20 release of the ARM software stack, it's now available on the Ubuntu Launchpad PPA. And it'll be a formal release in Bullseye, which is Debian 11. Now, the benefit of this is it's reliable, okay? All the build dependencies are taken care of by the robust Debian package infrastructure. And really, it's a really quick setup. Even I can do it, okay? It's ready for prototyping with just a few apt-get commands. And it's accessible. So the Ubuntu Groovy is now available for Raspberry Pi with full AR64 experience. So with Ubuntu, with Raspberry Pi, with ARM software and ARM-based hardware, you can get started running machine learning for a very cost-effective price and in no time at all. So it really is a nice solution. Okay. Next thing I'd like to mention is PyArmNN. And again, this is addressing a pain point for Python developers out there. And this really allows, rapid developing and prototyping. And these are essentially Python APIs for ArmNN inference engine. Okay, it's completely compatible with NumPy arrays, and there's minimal overhead. It's just a thin layer on top of ArmNN C++ API, and all computations are done by optimized ArmNN backends. And it's easy to install. It's integrated with the ArmNN build system, and it's available as part of the ArmNN Debian packages. So it's all available on GitHub. You can check it out there. And I've just put in a code snippet on the right-hand side, which kind of shows you the steps that you need to get up and running from loading your model file right down to performing inference and getting results back in a NumPy array. It's all there in this very small code snippet. Okay, so please check out PyArmNN. It's definitely useful, and we're getting great feedback from the community on it. The next thing I'd like to mention is the ARM public model zoo. So within ARM, we have a large collection of models across a broad range of various categories. And we felt it was time to kind of launch a public model zoo, which exposed some of these models to the public. And these are highly optimized networks specific to ARM architectures. Using clustering, pruning, and quantization-aware training, we get the most efficient models. The model zoo is located on GitHub, and there we provide the model, the metadata, and the test data, and the class labels coming soon as well. So it's all there for you to get up and running. And importantly, it's supported by code snippets. So there's an ML example section on our GitHub page. Check that out. That's linked to the models themselves. But importantly, we also have how-to guides associated with each of these models. And those how-to guides are continuously being updated on developer.arm.com, and we're adding new guides to developer.arm.com. On the right-hand side, I have just shown an example of some of the models we've released in the first phase. So SSD MobileNet, for example, version 1, this is a revised implementation with a 30% uplift improvement. MobileNet v2, we've done clustering and pruning in order to get better accuracy. WAV to letter is a speech-to-text model, and we've got 10x improvement there. DSCNN is a wake word model. And YOLO v3, which is one of the next generation object detection models, this specific model has been optimized for simplified classes and backbone, as well as detector quantization compatible. So this is a very interesting model, and it really is a nice take on the YOLO v3 generic models. So if you can, please take a look at it. And this YOLO v3 model, this object detection model, this is the one that we're going to feature in our demos today. Okay, so moving on to our demos. The first demo that we'd like to show you today is Inference on Linux using Raspberry Pi 4. So we're going to use a Raspberry Pi 4. I'm going to dial into it, but it's going to be similar to this one here. And it's a Cortex-A72 based CPU with 4 cores. And we're going to use the TFLite delegates in order to run machine learning on it. Okay. So we've got 2 tests on the left and on the right here, test 1 and test 2. And let me just give you a quick overview of the stack, which is depicted here. So first thing we're going to run is the TFLite model benchmark tool. And this is a really handy tool provided by TFLite. It allows you to do performance analysis, profiling, layer profiling. It's very useful. And using that tool then, we're going to use, first of all, we're going to use the TFLite CPU ref implementation, which essentially provides no acceleration. And that's based on the Cortex-A72. But then we're going to accelerate our neural network model through XNMPAC using the TFLite delegate. In test 2, what we're going to do is we're going to also use the TFLite model benchmark tool, but we're going to accelerate through the ARM software stack. And we're going to assess the performance of one stack versus the other. Okay, let me try and share my screen. Okay. Can you guys see a Raspberry Pi terminal?
Yes, we can.
Okay, so I'm logged into the Raspberry Pi here. And what I'm going to do is I'm going to run a number of commands. Okay, so let me, okay, this is a bit tricky. So first thing what we're going to do is we're going to call the TFLite model benchmark tool, and we're going to run a neural network through the TFLite CPU reference implementation. Okay. So I have a prepared command here, and let me copy that and I'll run it in the terminal. Okay, and as that's running, I'll explain the command. So the first thing you see here is we're calling the the benchmark model tool, and the graph that we're passing in is the YOLO v3 tiny darknet command. It's a floating point 32 model, and it's in TFLite format. It's important to say that we're executing this with 4 threads because it's a 4-core processor, and ArmNN by default runs 4 cores. Okay. So let's see how that's doing. So the inference is complete, and it took 507 milliseconds to run that command. Next, what we're going to do is we're going to run through it through XNMPAC. So again, now instead of running through the reference implementation, we're going to run through XNMPAC. So I come in here and I paste in the command. So the difference here is that we have now specified an accelerator. So it's the same command, except we're specifying an accelerator, XNMPAC equals 1. Okay, it's running through 50 iterations. The time we have to beat is 507 milliseconds. Takes a little bit of time. Okay, and this was much faster. It was 377 milliseconds. So you can see when you use the accelerator, it's much faster. What we're going to do now is we're going to run it through the ARM software stack. So I'm going to grab my command here, and I'm going to paste that into the terminal and explain what's happening. Again, it's calling the benchmark model, and it's calling YOLO v3. Excuse me. It's calling YOLO v3 darknet, so the YOLO v3 model from our model zoo, and it's using an external delegate now, which path is the libarmnn delegate.so, the shared object file, and it's passing a delegate option. So the backend in this instance is the CPU backend. So let's see how that ran. Okay, so that ran as an inference time of 248 milliseconds. So it's much faster than using the XNMPACK accelerator. I'd just like to say that we're using the Raspbian 64-bit OS in this instance on the Raspberry Pi. It's currently in beta, and we'll provide the link at the end of the presentation. Okay, so now we've seen that running it through the ArmNN, the ARM software stack, is much faster in terms of runtime. That was for a YOLO v3 model from the ARM Model Zoo, tailored specifically for the ARM architecture. But what happens if we take off-the-shelf TFLite model from the TensorFlow-Lite Model Zoo? So what we're going to do here is we're going to come back into our terminal, and we're going to take an Inception v3 model, okay? And we're going to run a very similar command, and we're going to check the performance. So again, this is you can see passing it through here. The model is Inception v3 TFLite. It's 4 threads, and it's running through now, and it's going to perform 50 iterations. And while that's happening there, I'll grab the next command. The next command will be to use XNMPACK accelerator. Just wait for that to finish. Okay, so this processed it in, let's see, is this right? 792, I believe. Yes, 792 milliseconds. Okay, so let's paste in the next command in. So what we're doing now is we're running it through XNMPACK. So with the TFLite CPU ref, it was 792 milliseconds. Now we're going to run it through XNMPACK and see how that performs. Again, it's going through 50 iterations. And you can see here the command use XNMPACK equals 1. Okay. So the time to beat is 792, and we can see here it's just under 600 milliseconds. So it's much faster using XNMPACK. Finally, what we're going to do is we're going to run it through the ARM software library. Again, the command is very similar. I've pasted it in there, and it's using the shared object file, which is libarmnn delegate.so, and the backend is CPU-ACK, okay, because we're doing CPU acceleration here. Okay, so we're hoping that it's less than 600 milliseconds, and the time is indeed less. It's 387 milliseconds, okay? So what that shows is that these are approximate timings here taken from previous runs, but basically we performed a number of tests, and as you can see, when you're using no accelerator, this is the performance which you see here. If you use XNMPACK, it's slightly faster. But if you use the ARM software stack with ArmNN ARM compute library, it's much faster again, 246 milliseconds and 385 milliseconds. So what this shows is that using YOLO v3 model from the ARM Model Zoo, you get a 1.5x speed up using the ARM software in comparison to XNMPACK. But if you use an Inception v3 model off the shelf from the TFLite Model Zoo, you get 1.6x speed up over XNMPACK. Okay, so that is acceleration using the ARM software on CPU. Let's take a look at GPU. Okay, so in this instance, what we're trying to do is it's very similar to previously, except we're going to do inference on Android. And we're going to examine the performance on Mali G77 GPU. So we're using a partner's flagship smartphone here for the purpose of this demo. Now, the good news is that the stack is quite similar. We're still using the TFLite model benchmark tool, TFLite CPU ref, but this time we're using the TFLite GPU delegate instead of XNMPACK, and we're running it on a Mali G77 GPU. And here on the right-hand side, we're using the ARM software stack, again with the Mali G77 GPU. So if I flick back to not this terminal, but this terminal here, excuse me now. Okay. Okay, so I am logged into the device, and I just want to show you briefly what is located in this folder. I didn't show you on the Raspberry Pi, but it is the same. You have the model benchmark tool, which is at the top of our stack. And then you have the lib-ArmNN SO, which also contains the compute library. Then we have the lib-ArmNN Delegate shared object file. And then you have the lib-TensorFlow-Lite shared object file. And we're packaging these up, and we're going to provide them on our GitHub page with our upcoming release, the 2102 release at the end of this month. So you can grab these yourselves and get up and running very quickly. Also on in this folder, we have the Inception v3 file, which is the one off the shelf from TensorFlow-Lite. And we also have the YOLO v3 tiny model from our Model-Zoo. Importantly, because this is a GPU, we also have a tuner file, which provides improved performance because it's tailored towards that device. Okay, so let's get to it. So what we're trying to do is we're going to do similar to before, except we're doing it on GPU. The good news is the stack is the same, the commands are very similar, and it runs faster on GPU. This time we won't run the reference implementation, we'll just run the TFLite delegate. So let me grab this command here. I'll paste it in, it's running there. And I'll explain what it is doing. So it's the model benchmark tool, the graph is the same, it's YOLO v3. We're saying it's to use the GPU equals 1, and it's saying don't run in floating point 16 mode and don't allow a precision loss. So we're running this at FP32 mode, floating point 32, in order to ensure precision. Okay, and after 50 iterations, you can see that it's processed in 47 milliseconds. Okay, so just to recap, that's going down through TFLite GPU delegate. Now, if we come along and we, if we come along and we run it through ArmNN, we paste that in there. Again, the command is quite similar to previously. You're using an external delegate, lib-ArmNN delegate.so, and there's a delegate option here. You're saying use the GPU backend, and importantly, you're instructing it to use the tuner file, tuner.csv. Okay, so we want to beat 47 milliseconds, and we can see that this completes in 27 milliseconds. So in this instance, when doing inference on ArmNN, it is faster than the TFLite GPU delegate. So how about an off-the-shelf model, Inception v3? We grab this command. Okay, so it's going to go through 50 iterations. And you can see that it runs in 108 milliseconds, okay? How about if we use the ARM software stack? So hopefully it's faster than 108 milliseconds. Again, calling the tuner file and the GPU backend. And we can see that this completes in 49 milliseconds. Oh, here, yeah. So after 50 iterations, it's 49 milliseconds. Okay, so what this shows then is that when we're doing inference on GPU, what we can see is that similarly to previously, we can see that the ArmNN software stack performs better than the TFLite GPU delegate in terms of minimum execution time. In fact, when you're using YOLO v3, it's a speed up of about 1.7x. And when you're using an off-the-shelf Inception v3 model from TFLite, the speed up is 2.2x performance speed up over the TFLite GPU delegate. Okay, so I think what we tried to show today is that we've added a lot of new usability features, which should address a lot of pain points and really get developers onboarded very quickly. And we're continuously providing new performance optimizations on key operators in various networks in our ARM compute library. And I hope that this demonstration shows the performance gain that can be achieved when using the ARM software stack and how it can be easily plugged into your existing tools. There's no messing around. It's very simple. Okay, so I just like to point you to a couple of useful links. If you're using Android, please check out ArmNN HAL for Android. It's available on our GitHub page. If you want to use TFLite either for Android or for Linux, that's also available on our GitHub page, the TFLite Delegate. Remember that we'll be putting the shared object files up on the GitHub soon with the imminent release of 2102. The ARM model zoo, we've a first instance of new models up there at the moment, and we'll be adding to that with each iteration, including embedded models in the near future. The ML examples accompanies the model zoo, so there's code snippets there to help you get up and running with those models. And please do check out the how-to guides, because we're going to be adding more and more guides there. There's guides there already on object detection and with web to letter and a couple of other guides, so check those out. Again, if you're using Raspberry Pi, which is really, I recommend it for getting up and running, you can use the Ubuntu for Raspberry Pi or the Raspbian for Raspberry Pi, and this is 64-bit versions in beta release at the moment, but really it allows you to get set up very quickly in a cost-effective manner. And it's important to remember that our software stack is open source, like a lot of ARM software. If you feel that you're getting value from our software, please consider adding value and contributing to our ARM software stack at mlplatform.org. I've just listed the SHA versions for the various software that we've used today if you want to check those out on GitHub. Okay. So if there's any Q&A, I think now's the time. And I chose this slide because I thought it was appropriate for the way we are working today. So please, guys, if you have any questions, let us know in the chat.
Yes, there are questions. There's a few. Sorry, I've been trying to answer some of them while we go through. At least the ones I can answer. Here, let's go with the first one we have. Can you recommend any development boards similar to Raspberry Pi except for GPU inference? I guess any like good development boards that have a GPU that supports ArmNN.
Yeah, sure. There's one, the Odroid N2, which we use internally. It's got is a Cortex-A 73, but it's also got a Mali G52 GPU, and it's often used by our internal development time. It's a similar price range to the Raspberry Pi, so yeah, that's a suitable option.
Okay, great. Let's see. There's been a lot of questions around unsupported operations. Can you just go into a little bit more detail about how the TFLite delegate works? Here, let me give you a specific question. Are the unsupported operations that run through TFLite optimized using quantization, etc.? So if you're using the TFLite delegate, is there any extra optimization, or is that just, how does that, like, what mechanism is that running?
Jim, why don't you come in here and see, can you get a grab on that one?
Well, if I understand the question correctly, you're asking, is there quantization done on the fly, maybe?
I think so. Like, is the TFLite delegate doing any different operations than running on those layers that aren't supported in ArmNN, or is it just running the TFLite inference stack?
So any operators that ArmNN and compute library support will be executed through the ArmNN CL stack. and it will be handed into, so there's the TFLite interpreter runs in 2 stages. First of all, it asks the delegate which operators it runs, and then partitions up the graph into subgraphs, the ones that will run on the delegate and the ones that TFLite will run, the ones that have operators that aren't supported. So the delegate gets handed not operator by operator, but it gets handed a graph, a subgraph of the overall model. And then one of the first operations that happens when ArmNN looks at that graph is it will apply a set of optimizations. So if there are ways that it can fuse operators or it can eliminate layers that are not necessary to the computation, it will do those optimizations before it does start to execute. But in specifically when it comes to the quantization, the model itself has to be, before it gets anywhere near TFLite, has to be quantized. There's no quantization that's done on the fly. The model is either going to be, it's going to be whatever data type it's been set up to be. It's either going to be an FP32 or an FP60. Well, we can actually downsize it from floating point 32 to floating point 16, but at present there's no way to quantize it on the fly. Quantization is something that really should be done at training time in order for it to work optimally.
Or post-training.
Yeah.
Awesome. Great. Yeah, that was a fairly complex question, but it was a good one. Okay. Here's one on terms. Here's one for open source contributions. What kind of open source governance model does ArmNN have? How would my team go about contributing and getting patches upstreamed?
Jim, that's squarely in your zone again.
Yeah. So we have an open Gerrit review system up on ML platform. So for historical reasons, we release every 3 months on GitHub, but our development is done in the open on ML platform, which is hosted by Linaro. So every commit that we do is basically put out on Gerrit and is immediately publicly visible even before it gets merged into the master branch. So you are completely free to do a git push to that repository, and any commit that you put up there will be reviewed by the ArmNN team, and once it passes the developer review, we'll then run it on the. There's a bit of logistics to do with getting it to run on our internal build system, but once it's passed to be secure enough, it'll go in, get run on the internal build system. Any build failures and stuff, we will either help you to fix or we'll show you what's wrong and get it fixed there. And yeah, once it goes through review and test, it will be merged in. I mean, we have contributions now from quite a number of different people. In terms of, I mean, we're not 100% there yet, I would say, in terms of the design direction and the whole direction that we're going in. I think we'd like it to be more open, but that's still a work in progress. But we're completely open to contributions coming in from anywhere, basically, so long as they fit, so long as they're up to quality level, and so long as they fit with the general technical direction of the product.
Yeah, and I think it's fair to say that community of contributors is growing as well, so that's good to see.
Yeah, and it's something we're really eager to encourage. So we're open for business.
Great. Another, let's see, this one's going to be very specific. Does the ARM64v82-A Arch option in ACL enable dot product support, or is dot product only enabled if using ARM64v82? Let's see. It's difference in the branches, basically.
Gianmarco, can you come in on that?
Yes, with pleasure, honestly, because this is an interesting question and is going to help me also to highlight one of the valuable aspect within ACL, because actually for using the dot product, it's not necessary to pass the dot prod to the architecture pass at compilation time, because this feature is basically detected at runtime by the ArmCompute library. So what does it mean? It means that even if your compiler, for instance, doesn't support the dot product instruction, the ArmCompute library is still able anyway to call the optimized routine with the dot product instruction, because most of the routines are written in assembly. So this means that, for instance, if we have a new features coming which is not supported by the compiler, anyway, the compute library will be able to exploit this feature because we have the assembly routines written. So regarding the questions posted here, I can say that you can simply use the ARM64 v8-A without passing anything else to support the dot product. Of course, if you spot any issues or the dot product is not detected, I mean, you can for sure post the questions on GitHub and we can have a look. But usually we are agnostic, so it doesn't depend on the compilation. So on the compiler, we are able to use ACL even if we don't pass this information.
Awesome. Lots of questions around TFLite parser for ArmNN versus TFLite delegate. So one of the questions is, will TFLite parser still be supported in the future, or TFLite delegate is the way to go now?
Yeah, that's a good question. I mean, we still support a TFLite parser and we'll continue to support it, but we'll be doing a lot of our optimizations focused on the delegate itself. Jim, any comments on that?
Yeah, I would say that when we are putting in support for new operators, we'll put it into the delegate first because that's where we'll get the biggest payoff. And we will be backfilling then the TFLite parser. So we will be pushing the TFLite delegate as the way to go if that's possible.
Yeah,
Great.
and of course we added new operators to NN API as well.
Yeah,
or NN
we're trying to ensure that the TFLite delegate and the NN API operator coverage is as equivalent as possible, so that you're not making a compromise if you're choosing between either of those options when you're deploying on Android.
Yeah, good point.
Cool. Yeah, that was also going to be another question. With so many choices, which one do you pick? Either. It's whatever you're most comfortable with then, right? Let's see. Can we use delegate feature to distribute subgraph processing from a TFLite model? I guess that answer is yes.
Yes.
Got that one. Here's a question in terms of performance drops, if they exist, in terms of accuracy. If TFLite converts a regular model to a lower resolution, is there a further drop in accuracy for the gain and inference speed if you're using any feature within ArmNN, or is there no loss in accuracy?
It depends. I mean, there's always a trade-off depending on what is the best solution for you. Jim or Gianmarco, do you guys want to comment there?
Probably I can answer this. So if I understand correctly the question, so basically if you're using a low limited numerical precision, for instance, we have a reduced accuracy. So it could be. For instance, I can tell you that there is, when we talk about the data types for ArmNN and ACL, we have usually floating point 32, we have floating point 16, and we have also int8 quantization schemas. For the floating point 16, for instance, we also provide a fast math flag, which is basically an option for the developers. What does it mean? It means that if it is enabled, yeah, the performance can be improved. but the accuracy can be reduced. But of course, we are not sure about it because it depends on how the network has been built, if the network has normalization layers. So in those cases, usually ArmNN is able to give the possibility to the developer to decide to turn on or turn off specific optimizations to reach the desired performance or the desired accuracy.
Yeah, so and if you're interested in improving your performance using FastMath, there's an excellent blog on our website. Do check it out on developer.arm.com.
Great. There's a lot of questions around what boards and what specific chips and are supported. Is there a good guide anywhere in terms of here's all the things that ArmNN is working for, or is there a good rule of thumb to go by for, say, looking at like a smartphone or single board computer that you have on your desk and saying, oh, ArmNN will work with this?
It'll work with most, I mean, Cortex-A big or little CPUs, it'll work with all Mali GPUs. And if you're targeting the Ethos-N, it'll work with those as well. In terms of target boards, you've got the Raspberry Pi, the Hikey 960, the Odroid N2. Guys, any further comment?
Sorry, I was looking the unmute button. So yes, I would say that every time we have an ARM processors with at least a Neon engine, well, it should work. So ArmNN and ACL should work out of the box. The minimum requirement is, in fact, the Neon vector engine support.
And correct me if I'm wrong here, Gianmarco, but is it from version 7 onwards?
Is from AMV7, of course, with Neon support.
Yes, with Neon support, yeah.
Got it. Everyone, please keep the questions coming, but we still do have some more. Can you explain the significance of the tuner file that was used with the GPU commands? Is it for performance improvement?
Oh yeah, that's a very good question. And yes, it is for performance improvement, and it's related to local workgroup size. Gianmarco, can you take this question?
Sure, I can. So the OpenCL tuner file basically contains the most suitable or best local workgroup size value for each OpenCL kernel dispatched by the ARM Compute Library backend. As Ronan mentioned before, this has a huge performance benefit. We have experimented in some cases over 30% performance boost. There is also an interesting blog written by our colleague Roberto on this topic, and I suggest to read it. If you ask me why the LWS can improve the performance, the reason is behind the way we dispatch the OpenCL job on the GPU. So basically, when you want to control the, so when you run the OpenCL kernel on GPU, there are two main aspects behind the OpenCL scheduling. One is the work item, which is really similar to the concept of threads we have on CPUs, but usually on GPU you have thousands of threads. And you have the local workgroup size, which basically defines how many work items must be executed on a same GPU core. This has an impact, of course, on the efficiency of how we access the elements in memory, and that is the reason why the OpenCL tuner file has this such performance benefit for ArmNN and ACL.
Hey, Gianmarco, as well as the LWS tuning, I think it's important also to mention the gem heuristics that we have built into the code for the most common SoCs that exist out there today. Can you talk about that a little?
Sure. So this is one of the reasons why, for instance, the performance on CPU and GPU in particular is pretty good. Is because we have handcraft heuristic for each Mali GPU's architecture that you can find within the ARM Compute Library. And so this means that basically the gem routine, which is at the heart of the most of the convolution layers, is tuned in a way in order to exploit the best performance on your Mali GPUs or Cortex-A CPUs.
Okay.
Okay. Thank you. Yeah. Are there any other questions right now? We probably have time for one or two more, given what time it is. I do have another one. Let's see. The inference on GPU seems to be 8 to 10 times faster than that of CPU. Why is there such a large difference?
Yeah, that's a good question. If I show here, you can see that in demo 1 on CPU, the inference, say for ArmNN with YOLO v3 is 246 milliseconds. And okay, yeah, it's 26 milliseconds here. John Marco, you can answer that question. I could give it a go, but I know you'll answer more succinctly.
Hopefully. So the straight answer is because the configuration of Mali G77 we have is much more powerful in terms of arithmetic capabilities compared to the Cortex-A72 that we have on Raspberry Pi. This is the straight answer. Of course, we need to remind that ARM is an IP company. So this means that ARM designs IP, which are can be customized in terms of CPU cores, in terms of GPU cores. And of course, it depends on how the configurations have been built. So that is the reason I use the word configuration of Mali G77 before. But that is the answer, simply because it's much more powerful in terms of arithmetic capabilities, the configurations we are talking about.
Yeah. To be fair, the A72 is a little older as well, right?
Yes, it is.
With that, I think, let's see, let's do one more question. Since we've gotten a few questions in terms of deployment strategies and is there any runtime support for PyTorch models?
Yes, we do have support for the Onyx runtime. So we've got an execution provider for ArmNN, and you can check that out on the Onyx runtime website.
Okay. With that, I think that was a quick answer. Let's see.
Jim, do you want to elaborate on that one, or is there anything else to say?
Just that we're continuing to look at PyTorch and see what technical options are available to us there. That's a very quickly evolving platform, and at the moment, the only way we have to support it is via export of the model as Onyx. There's not as much infrastructure provided within the PyTorch ecosystem for plugging in accelerators as there is in TFLite, but it's something we're continually looking at. It's not because we don't want to, it's because yeah, there are technical challenges there that we're continually monitoring and trying to figure out what's the best way of supporting PyTorch as well. I mean, we want our hardware to shine in every framework. So
yeah,
watch
excellent.
this space, I suppose, is our answer.
Yeah, I think there's a few questions around that, and I would say with the nature of machine learning frameworks is that change is always there. So we have lots of teams working in ARM in order to make sure things will be as optimal as possible, with whatever toolkit you're looking at.
Indeed.
I think that's all the time we have for today. Thank you, our panel. Thanks for the demo with ArmNN. Make sure to fill out our survey, sign up for the next virtual tech talk, and definitely check out all the resources that Ronan showed around ArmNN. And if you are working with ArmNN, feel free to start contributing. that's always really good to start building this as a big open source tool that is good for everybody. And with that, thanks everyone.
Thanks everybody. See you next time.
Thank you.
Thank you.